In this lesson, we're going to be talking about vertical motion. This is going to be the second part to the vertical motion equation. Remember that this is your vertical motion equation. The negative 16 represents gravity, t represents time, v naught represents initial velocity, and this represents initial height. And the y value is your height with respect to a specific time. So remember that this is a vertical motion, so an object is going straight up in the air and coming straight back down. We're not shooting anything on an angle, it's vertical, so it shoots up, comes back down. So the situation that we have is a ball is thrown straight up into the air with an initial velocity of 112 feet per second and an initial height of 6 feet. So these are the types of questions that we're going to ask. We're going to get a little bit of a visual of what this might look like, and we're going to try and solve these questions. So first question is, what is the maximum height the ball will reach? When will that maximum height occur? What is the height of the ball after 2 seconds? Is the ball traveling up or down? What is the height after 4 seconds? Is the ball traveling up or down? And when will the ball reach a height of 150 feet? And when will the ball hit the ground? So these are the things we're trying to take care of. And we want to kind of generalize rough ideas of how we go about doing this. Anything that relates to a maximum, anything maximum related, is all of this is going to be talking about the vertex. All right, so it's the highest point, which is the vertex of our quadratic. All right, so we're definitely having a quadratic. It's negative, so the quadratic is going to go down, and we're going to have a maximum to it. So that relates to vertex. Anything where they ask after so many seconds, so a specific time has elapsed, that's basically telling us that that t is going to be replaced with the question that they're asking. So anything with a specific time is you are just going to plug in time. All right, so those two are relating with specific time. We'll just plug them in and we'll talk about how we know whether the ball is traveling up or down. And then anything where they're asking a question of when does a specific ball hit a specific height, we're looking for the when, which means we don't know the time, which means we must know the height. So we're going to take this equation and set it equal to the specific height and solve. So these two are going to set equal to height and solve. Okay, we'll see how that happens. All right, so rough visual of what we have going on is, let's create our equation. And our equation is height with respect to time equals negative 16t squared plus an initial velocity of 112 feet per second plus an initial height of 6. So we'll come back to this. We're going to get a little bit of a visual, do some solving, and see what we got. So this x-axis is going to be representing time, and the y-axis is our height with respect to time. So if we were to look at this equation, it has an initial height of 6, which is also our y-intercept. So we have some sort of a height of 6. All right, and it is a quadratic, and this object is going to go up, come back down, but as time is elapsing, and it's not the path, but this is the look with respect to time. So as time is elapsing, the object goes up, the object comes down. So the object goes up, as time is elapsing, the object comes back down, hits the ground. All right, so the types of things we're looking for is, we're looking for the vertex. What's the highest point? We're going to then mark that down of what that highest point is. And we're looking for a couple questions of, is the ball traveling up or down after 2 seconds? Where is it? How long does it take to hit back to the ground? If we do hit a height of 150 feet, how long does it take for that to happen? All right, so we'll come back to this visual. We'll add some things to it as we go through, but now we're going to do some of the math to it. right, so first question was, what is the maximum height? So maximum height relates to vertex. So we're going to need to find the vertex on this. So to find the vertex, we have a formula for this. And let me write down our equation first. So it's negative 16t squared plus our initial velocity of 112 feet plus our initial height of 6. So our vertex is normally x equals, except our variable is t. So we'll put t equals negative b divided by 2a. So our b value is 112, so it's negative 112 divided by 2 times a, which is negative 16. So that is going to be negative 112 divided by negative 32, which ends up equaling 3.5. Now that's our time that it takes to get to the maximum height. We don't know what the maximum height is, but we have this equation. That is, if we know the time, we can plug it in, and that'll find us our height. And this is going to be the maximum because it's the vertex. So our height with respect to time, we're going to be plugging in a 3.5. So that's negative 16 times 3.5 squared plus 112 times 3.5 plus 6. So height after 3.5 seconds is going to equal 202. So our vertex is 3.5, 202. And so just if we understand the pieces to this, this is the time that it takes to get to your maximum, and this is the actual height. All right, so now we can actually answer the question. What is the maximum height the ball will reach? The ball will reach 202 feet. When will the ball hit the maximum height? At 3.5 seconds. Okay, so we can also connect that to the graph. So we'll come back. And we have a maximum height at 3.5 seconds. It hits a maximum height of 202. All right, so this already starts to answer our question of after 2 seconds. Well, 2 seconds is over here. Whatever that height is that we get, is it going to be traveling up or down? Well, it's going to still be on its way up. And after 4 seconds, which is just past our vertex, we're going to be traveling down. Okay, but how do we figure out what the height actually is after 2 seconds? We're going to plug it in. So we're going to come back to the graph, and let's plug it into the equation. All right, so this was part A and B. Part C is we're going to find the height after 2 seconds. So negative 16 times 2 squared plus 112 times 2 plus 6. That height after 2 seconds is going to equal 166 feet. Then if we do the exact same type of thing for D, our height after 4 seconds is same equation. Plug in 4 plus 6. So our height after 4 seconds ends up being 198 feet. Which seems right because 4 seconds is just after the vertex. The maximum height's 202 and we're just on the way down, so it should be close to the vertex. So we have 166 feet. For 2 seconds, we have 198 feet. for 4 seconds. All right, last two questions. When does the ball reach a height of 150? So for E, our specific height after a certain amount of time is 150. So I don't know what the time is, but I know what the height needs to be. So that means I can take our equation and set it equal to 150. And then we'll walk through the math. So this is a quadratic. I need everything over to one side so I can solve it. So I'm going to subtract the 150. So that's going to be a 0 equals negative 16 t squared plus 112 t minus 144. All right. I don't know if it's factorable. I'm not going to waste my time. I'm going to jump into the quadratic formula. So, and I'll, instead of putting an x equals, I'll put a t equals negative b plus or minus square root of b squared minus 4ac all divided by 2a. So I'll plug in my values. My b value is 112, so negative 112 plus or minus square root of 112 squared minus 4 times a, negative 16, times c of negative 144, all divided by 2 times a, which is negative 16. All right, negative 112 plus or minus. Piece on the inside here, if I add all of that together, that will get me 3,028 divided by negative 32. Okay, so all of that's 3328. This multiplies to negative 32. If I plug that into the calculator, I should get a value of about 1.70 and 5.30. Okay, so let me throw those answers down. Let's compare it to the graph, see if that makes sense. So we have a point of 1.70 seconds and 5.30 seconds. Okay, so why do we get two answers? Well, if we take a look at the graph will help us kind of make some sense out of this. So our graph looks like this. So 202 is here, so maybe 150 is here. Okay, not to scale. But the ball is going to hit on the way up at a height of 150 and on the way down. So this might represent the 1.70 and this might represent the 5.30 if you dropped it down and actually figured out what the time is. So it's going to hit it twice. It's going to hit it on the way up and it's going to hit it on the way down. So it makes sense that we get these two answers. So let's do the last one. The last one is, when does the ball hit the ground? Well, we need to know what the height of the ground is. So if it started on the ground, or the ground is basically a height of 0. It started at 6 feet in the air, so that's actually going to play a role here in a second. So F. The height with at a certain time is going to be 0 this time. Anytime you're ever looking for the ground, you're talking about a height of 0. So that means instead of setting our equation to equal to 150, because that was the height on the last problem, our equation is going to equal 0. So I don't have to adjust it. It's just ready to go. So I can jump right into the quadratic formula. So I have t equals negative 112 plus or minus the square root of 112 squared minus 4 times a, which is negative 16, times c, which is 6. All divided by 2 times a, which is negative 16. So that's going to be a negative 112 plus or minus square root of whatever this turns out to be on the inside, and it turns out to be 12,928. Plug it into the calculator. Divided by negative 32. So I'll plug that into the calculator, and we get times of negative 0.05, and we get approximately 7.05. All right, so problem is one of these doesn't make sense. We can't have negative time, so this answer doesn't make sense, and we'll look at the graph and see why that's even a possibility. The math just does the math. It doesn't understand that it's a word problem and you can't have negative, but this ends up being our answer. So 7.5 seconds. All right, so let's put that answer down and let's look at the graph and see if we can make some sense out of it. 7.05 seconds. All right. So the visual. Visual is this. It took us exactly 3.5 seconds to reach the maximum. So the quadratic is symmetrical, so it should take at least 3.5 seconds to come back down. If it takes 3.5 to go up, it should take 3.5 to come back down. But that would leave us at a time of where we started. We started at 6 feet, so 3.5 to get up, 3.5 to come back down to 6 feet, but we have to travel that extra 6 feet. That's why this value ends up coming not double this of 7 seconds, it takes 7.05 seconds. So that makes sense. Our answer should be really close to doubling the vertex. If it started at 0 rather than starting at 6, it would be perfectly symmetrical where it takes just as long to go up as it does come back down. But because we started at a little bit extra height, it takes a smidge extra time to go those 6 feet. All right. Second part of this is, where would the other x-intercept be? Because when you're looking for the height of the ground being 0, you're looking for the x-intercept, which was this one. But then the other one would be back here, and that would be our negative time. But that doesn't make sense. That's why we have to kick that one out. But that's where that piece would come from. So those are our answers. So anything that relates to a maximum, we're talking about vertex. Anything that says after so many seconds, what's the height going to be? Means just plug it in. And if they're asking for a specific height, then you're going to have to set your equation equal to that height and solve it. And most likely you're going to have to use quadratic formula to solve it. Not all the time, but far more often than not. All right, and that was vertical motion problems, part 2.